What's up, folks? All right, we're getting into this chapter 6 on thermodynamics. I hope I don't get banned on this song. I got bad luck of picking songs that YouTube doesn't like. Okay, awesome. Let's get it going. Definitely got to jam out to some Broken Bells later on in the day. Okay, so our chapter 6 learning goals. I've got them right here in front of me. On this first video, I'm going to try to get through the first 1, 2, 3, 4 of these learning goals. Definitely the first 3. Okay, so after I'm done, I'll come back here and review what we talked about. Okay, so let's put that away. Okay, so we're getting into thermodynamics. And to start, a few definitions, okay? So energy, heat, and work. So these are all things that you're probably familiar with, but we should discuss the appropriate thermodynamic definitions of these. So energy is defined as the capacity to do work, okay? And so the units can either be in joules or kilojoules. And so we remember that 1 kilojoule is 1,000 joules. So this is going to be our unit of energy, the joule or the kilojoule. So heat is the transfer of energy between objects of different temperature. And also the units are joules or kilojoules, okay? And so if we imagine this picture that I've got here, suppose I have one block that's 10 degrees centigrade and another block that's 50 degrees centigrade. Well, as soon as they come into contact with each other, heat will flow. And it's always going to flow from the hot object to the cold object. Okay, that's how this always works. So heat is the transfer of this energy from the hot object to the cold object. And if we wait long enough, both objects will eventually be the same temperature. And in fact, if both of these objects were made of the same mass and the same material, this 10 degree and 50 degree, they would actually both come to 30 degrees. We're going to do a calculation like this for objects of different mass and different material. So we're going to learn how to do this type of calculation. Okay, and finally, work is a force acting over a distance. So here's the equation where this is our force and this is our distance, okay? So again, energy, the capacity to do work. Heat, the transfer of energy between objects at different temperature. And work, a force acting over a distance. And note, all of these are either in joules or kilojoules, okay? We typically use kilojoules when our joules exceeds 1,000, and then it becomes convenient to write a kJ instead of 3 zeros, okay? Moving on. Okay, so potential energy and kinetic energy. So we've talked about energy, but as it turns out, there's 2 flavors of energy. There's potential, and that's the energy stored in an object because of its position, or as we shall see, even its composition. So right here, we can see that this skier in this position has a lot of potential. It has a lot of potential energy, okay? But we shall also learn that some materials don't have to be like way high up on a hill to have a lot of potential energy. Their chemical composition can actually have a lot of potential energy, okay? So kinetic energy, the energy of an object in motion due to its mass and speed. Okay, so now this skier is converting that potential energy into kinetic. And so by the time they get down to this position here, they will have spent all of that potential energy in the form of kinetic energy, okay? So the skier will be moving, the fastest, maybe at this point right here, they would be moving the fastest, right? They fly through the air and then gravity takes hold. But in any event, we should recognize, if we look at the skier's initial state, which I'll represent with an I, we're going to see that a lot, and the skier's final state, we kind of view potential energy in this type of a diagram, right? Okay, so moving forward. So here is a little bit more on potential energy and the law of conservation of energy. Energy cannot be created nor destroyed, but it can be converted from one form to another. So that's just what I was talking about, how the skier is converting its potential energy into kinetic energy. Okay. Also, there's another important topic to discuss on this notion of going from the initial state to the final state, you know, something like this, initial and final, okay? So we call a property a state function when it is path independent, okay? So only the final state and the initial states are important when something is a state function. And as it turns out, energy is a state function. There are other properties that are state functions, but energy is definitely one of them. And to give us a clear sense of what is a state function, we use capital letters in the symbols for state functions. So for example, I would use a capital E for energy to indicate that it's a state function. And so what do I mean that the initial and final states are the only thing that's important? Well, let's look at two possible paths a skier might take, okay? So they might take the ski lift, right, all the way up. And just to make this an equivalent argument, I'm going to label, you know, initial state and final state of both skier 1 and skier 2 right here, okay? And so we also note on this picture, the mass of skier 1 equals the mass of skier 2. So they're the same mass. So suppose maybe it's the same person, and in one ride, they just went down the ski lift and, or I guess this figure is showing us that they went up the ski lift, right? And this other ride, like a crazy idiot, they climbed up this hill instead of skiing down it. In any event, okay? So I suppose I could change the I and F to make that consistent with our story. So apologies. We'll make this the initial and this the final. So for both of those paths or skiers, however you want to look at it, the change in potential energy is the same, okay? Whether they took the ski lift or whether they hiked all the way up, right? Their initial state and their final state was the same for both cases. Now, I think we could easily argue that the work that the skier did is vastly different from path 1 to path 2. And that is correct because work gets a lowercase letter w, as well as heat. Heat gets a lowercase letter q, okay? So these two quantities are both path functions. So for heat and work, it does matter how you do it, right? This skier climbing up this hill is going to be doing a hell of a lot more work than this skier taking the lift. However, both of them will have overall the same change in potential energy. So we kind of have to wrap our heads around that, okay? So state function, only the initial and final state matter. Path function, the path definitely matters, okay? And again, we use capital letters in thermodynamics to indicate what's a state function. We use lowercase letters to indicate things that are path functions. All right, moving on. So here's another form of energy, and that's called the electrostatic potential energy, okay? So notice that it is a form of potential energy, but whereas this is really gravitational potential energy, right? This is the potential energy due to gravity. We can also have potential energy due to electrostatic. So in other words, the attraction of opposite charges. So positives and negatives attract each other, And based on the position of those positives and negatives, they could either have a lot of electrostatic potential or no electrostatic potential. So for example, and so again, this I should say again, I'm introducing this for the first time. Potential energy, electrostatic potential energy, is kind of the opposite of gravitational potential. So for example, if I'm holding an object like way up high, it has a lot of gravitational potential energy. However, if I have two charges that are separated really far from each other, they have no electrostatic potential energy. So for example, right here in this picture, where we see this large distance between the positive and the negative charge, I had a crazy little thing that happened there. Okay, so there's a fairly, let's say, large distance between the positive and negative charge. And on this graph here, this distance, look, this is distance on the x-axis and this electrostatic potential on the y-axis. So they have zero potential energy between the two. However, as they start to get closer to each other, they end up having a negative electrostatic potential energy. And the way we define this, a negative electrostatic potential energy means they're more stable. Okay? And so we eventually are going to get to this spot. I like to call this the sweet spot, where the positive and the negative are at this, let's call it a magic distance, a little sweet distance right there, where the electrostatic potential has come to a minimum. Okay? Well, this sweet spot would give us the bonding pattern between those two ions, right? If this were an ionic compound, right, a cation and an anion, this is the distance those things would exist. Whatever this distance c is, right, whatever that bond distance is, it would give us, how far those things are apart based on their electrostatic potential. And of course, if we get them closer, if we force them to be closer, they will start repelling each other. And they'll start repelling each other because we have to remember, even those negative charges, those negative anions, right? They still have a nucleus. And that nucleus still contains protons and neutrons. Okay? So eventually, if we try to push things too close to each other, they will repel. All right? So that's our sweet spot based on the electrostatic potential. Okay? This is true for ionic compounds, but this is also true for covalent compounds as well. So there's a sweet spot based on electrostatic potential of covalent compounds. So moving along. So another form of energy, thermochemistry. Okay? And so now, if you notice my diagram here, this looks a lot like the skiers. Okay? So there's lots of chemical potential with a mixture of hydrogen and oxygen. So think about this, right? A mixture of hydrogen and oxygen is explosive. You just need a tiny little spark to make those things explode. I mean, there's like, I would do this for you all in the lecture hall. I have a sweet setup with a hydrogen bottle and an oxygen bottle, and we mix them together and make a balloon and light the balloon. It sounds like a shotgun when it goes off. I mean, you can feel it in your chest, okay? So there is a lot of chemical potential between a mixture of hydrogen and oxygen, or even between a mixture of methane and oxygen, or octane and oxygen. Think about all of the combustion reactions we've talked about. Those reactants have a lot of chemical potential. And when they go and react and blow up, that potential energy is getting converted into kinetic energy. Okay, so energy is being released. So if we think about this as the initial state here and the final state here, we come to an important conclusion, and that is, if I subtract the final minus the initial, which is always the case in a state function. It's always going to be final minus initial. Then we will actually get a negative quantity out of this. We will in fact see that the change in energy for this particular reaction in which energy is released is negative. And this is something we call exothermic. And we're going to see this in a coming slide here. So exo, meaning energy is released. Okay? And so again, we're going to view this in when we start to kind of build this up, this initial state and final state, we're always going to look at it as the final state minus the initial state. Final minus initial. Okay? And we're going to see, is that a negative quantity or a positive quantity? If it's a negative quantity, it tells us energy is being released. If it's a positive quantity, it's telling us energy is getting put in. And again, I'm going to review this again. We're going to see this idea coming up again. Okay? So let's talk about now system and surroundings. So this is really important in thermodynamics. And when we start to think about this idea, is energy being released or is energy being put in? We need to have a organized way of defining, well, what is it? From what lens are we viewing this? And the way we view that is system and surroundings. So in chemistry, it's all about the system. Okay? We are always defining what we can measure as the system. Okay? And there are several types of systems. 3, right? We have what's called an isolated system. And this picture gives you a good idea of this isolated system. In this isolated system, there is no exchange of heat or mass from the surroundings. Okay? So there could actually be, maybe in this thermos, right? So because this thermos is insulated and because it's closed, we can't put any mass in it and we can't exchange heat. However, there could be some chemical potential inside this thing. So we could put a reactive bunch of molecules in an isolated system, and they could do a reaction which releases heat. However, that heat will be trapped in the isolated system. It won't make it out, okay? So we'd have to have some type of like thermometer or something in there to see what's going on. We have no idea what's going on inside of an isolated system. Okay, so now we have a closed system, and this is probably the most common type of system, the closed system. And in this closed system, there's no exchange of mass. But as you can see, as the picture is showing, heat can definitely get out. So the reason why this is the most common type of system we'll encounter in chemistry is because if you think about it, if you think about how we do chemical reactions in a little beaker, right? Maybe we put all the stuff in that beaker and then we step away from it. So we're not adding any more mass, but that beaker can definitely evolve heat back out to the surroundings. Or it could even take heat in from the surroundings, okay? So we want to really start thinking of now, so system, I use SYS as my abbreviation for system, and I used SUR as my abbreviation for surroundings, okay? So this is the system, and everything else around this is the surroundings. So if we have this hot bowl of soup as our system, heat is leaving it. So it has a lot of potential in terms of heat that it can release. Okay? And then finally we have a wide open system. And in the wide open system, or just the open system, I'll just say everything goes. Okay? So not only is it free to exchange heat, it's also free to exchange mass. So like in making this soup right here, And continuing on with this diagram, we can add cheese or crackers or pepper. Like we could add mass to this system, okay? So keep track of those. Isolated, closed, and open, okay? So this is our most common in chemistry, is the closed system. But even so, as we discuss experiments called calorimetry, we try our best to make an isolated system in a calorimetry experiment. Okay, and I'll talk more about what calorimetry is in a later lecture. So moving on. So this is kind of a summary of everything that I've said. So when we do delta, so this is the Greek letter delta, and that means change. We use the Greek letter delta to indicate a change. And specifically, it's always final minus initial. Always. So I could have some other type of state function that I haven't defined yet, maybe capital X, right? Because capital letter tells me it's a state function. Whatever X is, pressure, volume, whatever, right? Temperature. It's always going to be final. So I'll say X final minus X initial, okay? So now, here we have the system inside this little box, okay? And then outside of the system is the surroundings. And outside the surroundings is everything else, the entire freaking universe, okay? It's a very boring world in this thermodynamics world here, okay? All the same, the universe is in contact with the surroundings, and the surroundings are in contact with the system. And in the case of this being an either open or closed system, right, because those can exchange energy, when energy goes from the surroundings to the system, as viewed by the system, the delta E of the system will increase. So in other words, the final state is now greater than the initial state. That gives us a positive quantity. We call this endothermic, meaning heat is moving into the system, okay? But as is the case, as is the opposite case, okay, when energy leaves the system and goes to the surroundings, then the final state of the system will be less than the initial state, and that will be negative. So heat is leaving the system and going out to the surroundings, which is why we call it exothermic. And so I already gave you one example of an exothermic reaction, combustion. All combustion reactions are exothermic, right? You light something on fire and it releases heat back out to the surroundings. So the fuel, the molecules that are burning themselves, those are the system. Everything else is the surroundings, okay? And so this gets us to now, I was just one slide ahead of myself. So just a little bit more on system surroundings and energy transfer with respect to phase transitions. As we might imagine, there are exothermic or endothermic phase transitions. You're already familiar with several endothermic phase transitions. So for example, how do you boil water? You put heat in, right? A pot of water will not spontaneously start boiling, okay? So that's this diagram right here, going from liquid to gas vaporization, right? Which, we could also call boiling. So heat has got to go in to boil that water, okay? Well, what about melting some ice? Yeah, you guessed it, right? An ice cube at 0 degrees Celsius will not spontaneously melt on its own unless you put heat into it. And that can actually be achieved by taking that ice cube right out of your freezer and setting it on a warm bench or countertop, okay? That ice cube, because it is colder than the countertop, right, back to that very first slide I showed you, right? If the countertop is 25 degrees Celsius and the ice cube is 0 degrees Celsius, okay, heat will flow from the hot object to the cold object, so it will melt the ice cube. Heat will go in to melt the ice cube. Similarly for sublimation, when you go directly from a solid to a gas, that requires heat to go in. But now if you think about all the opposite of these, I think these are all less intuitive, okay? So back to that freezing example now. If we want to freeze some water, for example, we have to remove heat from it, right? We cannot cool things down by transferring heat from a cold object to a hot object. It doesn't work like that, okay? The heat has to go from hot to cold. So we have to remove the heat somehow, and that is achieved by the heat leaving the system and entering the surroundings, okay? Similarly with a gas condensing, okay? So if we know that we have to put heat in to boil something, when steam condenses, like you imagine maybe steam condensing on the windshield of your car, for example, that's going to release heat, which you don't really think about. That's counterintuitive, but it will in fact release heat out to the surroundings. And we'll explore more of why that is in Chem 110. We'll get into those details and a lot more when you take Chem 110. It has to do with the second law of thermodynamics. But now we're getting into the first law of thermodynamics. And the first law of thermodynamics says, don't talk about thermodynamics. Just joking. That was a Fight Club joke, if you've seen that movie or read the book. So the first law of thermodynamics says the energy of the universe is constant. So that's one way to view the first law. The mathematical definition of the first law is the following. Delta E, right, which we remember delta E is E final minus E initial, equals heat plus work. Okay? So we talked about how energy can be exchanged from one form to another, right? So in this conservation of energy, or in other words, the energy of the universe being constant, we can't create more energy, but we can exchange it from one form to another. Heat and work can definitely be exchanged. So we can provide an engine with heat and it will do work for us. Okay, this is how your car works, right? You're burning all of that fuel, you're releasing heat from a combustion reaction, and it's driving this piston to move up and down, which causes a drivetrain to rotate, which causes your tires to move, so on and so forth, okay? Other ways to view the first law, so this delta E can refer to system or surroundings. However, if we now put specifically system or surroundings, we could always view that in the case, because energy of the universe is constant, the energy of the system, change in energy of the system, will always be the negative change of energy of the surroundings, right? Equal and opposite. Or E system plus E surroundings equals 0. Okay? So in other words, if my system gives off heat, then perhaps the change in energy for the system is negative, but then the change in energy for the surroundings will be positive. Okay? So this is just saying kind of what we saw in this diagram, right? That the heat flow will be opposite depending on if you view the system or the surroundings. In chemistry, we're always interested in the system. All right? So now, what about work and heat? Okay. Well, so we just talked about when delta E is negative, heat is leaving the system. And when delta E is positive, heat is, or I should say energy rather, energy is entering the system. But what about heat and work specifically? Okay, well, so here's another diagram where we have surroundings in yellow and system is this little green circle. So when heat moves into the system, we say Q is positive. So positive heat, positive Q means heat is going in. However, work can be done on the system too. We can do work on the system. And that would be in the form of a force acting over a distance. So remember, work is force times distance. And the easiest example of this that we're going to see in the next slide is compression. So imagine taking a balloon and we're forcing that balloon to be smaller. We're working on the balloon. We're pushing it, okay? And so because that's work being done on the system, as is showed in this blue arrow, work would be positive, okay? So whether we have heat going in or work going in, and specifically going into the system, those quantities will be positive. Now, what about the opposite? What if we have heat leaving the system, such as the example of an exothermic reaction? Well, we would say Q is negative. Okay, so the opposite of heat going in. When heat is going out, it's negative. Or when work is being done by the system, it's also negative. And if we think about this, if work being done on the system might be compression, squeezing that balloon down, okay? If instead it's the opposite case, if it's expansion, if perhaps our balloon is now expanding, it's actually pushing away the atmosphere, right? It is pushing the surroundings out. And so we call that negative work. We say the system is doing work on the surroundings, okay? So keep track of all of these things, system, surroundings, etc. Okay, let's do one example problem, and I think that'll be good for the end of this lecture. Okay, and so this is specifically now, so this is a new type of problem that we've done here, and it's a type of problem where we're going to calculate work. So we're going to start doing problems now where we calculate work, we calculate heat, and then eventually we can calculate the change in internal energy. Okay, so I just talked about how expansion work or compression work can be viewed as exothermic or endothermic. So compression work, right? So if let's say I define now what's inside my piston as the system, okay? Then now this is positive work that's being done. So the surroundings are working on the system for compression. But now, so look at this, fuel explodes. So this is how I know I'm able to define what's inside the system, what's inside the piston as the system. This can be hard at first. How do I get the system and surroundings correctly? It kind of takes some practice, all right? So, but I call what's inside this piston the system because there's fuel that has chemical potential. That's right, we're going to connect all of this. So the fuel that's inside this engine has chemical potential to be used by the system to do work on the surroundings. So now the fuel explodes, that causes an expansion, and so then that's now negative work because the work is being done on the surroundings by the system, okay? And the equation that we use to calculate that for pressure volume work is P delta V, where yes, delta V, as you might guessed it, being a state function, capital V, which is V final minus V initial. And what I want to point out here is in the case of, let's go through this compression case, okay? So we would say work equals, and I want to talk about this negative sign. Pay attention, there's a negative sign in this equation, okay? And why is that negative sign there? Well, I can rewrite the equation as work equals negative P times VF minus VI, okay? And in the case of compression, we have to think about the initial volume and the final volume and how they're going to be related to each other, okay? So we imagine this initial volume was probably down here somewhere, right? Like I'll draw a little line. And, you know, this is likely what the initial volume was, this whole thing. And so now it's being compressed, so the final volume is smaller, right? So we can say that VI is greater than VF in this compression situation. And if that's the case, if VI is greater than VF, then look what's going to happen. So this VF minus VI will be negative, right? And then times negative P. So negative times a negative gives me a positive. Okay, let me write that multiplying sign better. So that's why we have the negative sign in this equation, because it's just a convention we use. Compression work is positive. Expansion work is negative, and here's why. Negative P times VF minus VI, and then in this expansion, VF will be greater than VI. And because VF is greater than VI, this quantity is positive times the negative sign for the pressure. A negative times a positive gives me a negative. And so that predicts that work will be negative for expansion. Okay, now finally, what about the units? I've got this random unit conversion here because we talked about how work has to be in units of joules. But this formula is pressure times volume, right? So if I use this formula here, so negative sign, and let's suppose I use ATM for my pressure, and I use liters for my volume, which is, it's convenient to do so, then I'll have an atmosphere liter or a liter atmosphere as my unit. And that doesn't make a whole lot of sense, right? But I have this conversion here that says 1 liter ATM is 101.32 joules. It's actually 101.325 joules. Those of you that remember the Pascal unit from gas laws might recognize that number. That's where it comes from. It comes from the definition of a Pascal. But you don't have to know that as long as you know how to use the conversion, okay? So let's do one sample problem, and then that'll be good for this lecture, okay? So a tank of compressed helium is used to inflate balloons for sale at a carnival on a day when the atmospheric pressure is 0.99 atm. So I'm going to write that down. P equals 0.99 atm. If each balloon is inflated from an initial volume of 0.0, so we'll say V initial is 0.0 liters, to a final volume of 4.8 liters, so VF is 4.8 liters, how much PV work in joules is done on the surrounding atmospheres by 100 balloons when they're inflated? So let's calculate it for one balloon, okay? And so our formula is work equals negative P delta V. And so that's going to equal negative 0.99 atm. And then it's final minus initial, right? So that's 4.8 liters minus 0.0 liters. And that's some quick and simple math. So 4.8 negative minus 0 times 0.99. So I didn't do that in the right order, but all the same, it's still going to give me the right number. Okay, and with two significant digits, so that's going to be negative 4.8. And then the units of that are atm liter. Okay, and I know from my conversion factor that 1 atm liter is 101.32 joules. Right, so that's how I can use that, right? 1 liter ATM or 1 ATM liter is 101.32 joules. Okay, so now over here I can say, I'll leave the number in my calculator, right, for the best possible answer, times 101.32 equals, and now I get negative 481, and with my two significant figures still, that's going to be negative 480 with only two sig figs, okay, joules. And now that was only for one balloon, right? So I can do this with dimensional analysis by the following. I can say negative 480 joules per one balloon. And I know I can just say 100 balloons, and I don't have to put anything on the bottom right there, because that's just going to cancel the balloons, okay? And so times 100, I probably don't need to do this in the calculator, but I will anyways. Okay, great. So now I get negative 4.8 times 10 to the 1, 2, 3, 4 joules. And at this point, it's probably appropriate to use kilojoules because that's a pretty big number. Even though the problem said joules, that would be the right answer. But right, just to show you, 1,000 joules in 1 kilojoule. So we'll divide it by 1,000. Yep, or so I could say negative 4.8 times 10 to the 4th joules, or negative 48 kilojoules. Okay, so the math that we're going to see, the math in thermo is pretty simple. It's plugging and chugging into our equations. The hard part is going to be getting the units correct, as well as getting the sign correct. Is it negative or positive? Okay. So keep track of those. So let's see here. Where did my learning goals go? Let's see. I lost them. I will review those learning goals at the start of the next video. Okay, folks.